All right, Katie, number 3. Sure, this is probably easier than you're making it. But in number 3, what we're asked to do is to graph this vector. And this is actually, because it's really only got 2 components to it, is actually a pretty easy problem. So remember that the vector or the quadrants are x, y, and z. So vector x, the component is 0, right? So this is really just 2 dimensions in y and z. So 1, 2, 3, 4, 5 on the y, 1, 2 on the z. So there's my point, and there's my vector. Since one of the coordinates was a 0, it's really just a 2-dimensional problem, right? So it's not, you don't have to draw a box or anything. You really just have, your box just turns into a rectangle, so it's just like plotting on an XY axis. So it's no biggie. Easier than you thought, Katie?
Yeah.
I thought it would have. Yeah. 4? Sure. All right. So I'm going to start by drawing in some tick marks. So I need 3 tick marks on the negative x-axis. So that's the part that's like going backwards into the board. So that's the negative part of the x. And then 6 on the y. 2, 3, 4, 5, 6. And then negative 4 on the z. So there's that. Again, remember that x, y, and z are the names or the way we've named these axes. So I'm going to first start by locating the last tick mark on the x-axis. And I'm just going to draw a line that's parallel to the y-axis. Then similarly, I'm going to locate the last tick mark on my y-axis. And I'm going to draw a line that's parallel to the x-axis. What this does is it's going to create like the top or the bottom, depending on how you're kind of looking at it, of the box that I'm going to draw. Now, if I'm graphing in 2 dimensions, that's the point that I care about, right? Where I've gone 3 down the x-axis and 6 to the right on the y-axis. Everybody okay with that? But there's really a point at each one of these 4 intersections, at each of the corners. So what I'm going to do now is I'm going to find the corner that's located at the origin, and I'm going to project that corner down 4 units on the z-axis. Similarly, I'm also going to find the other corner that's on the y-axis, and I'm going to project that down 4 units on the z-axis. And then I'm going to do the same thing to the other 4, or the other 2 corners. I'm going to project those down 4 units on the z-axis. But here I just have to kind of estimate, right? I'm basically just going to try to draw a segment that's the same length as the other segments that I've just drawn. So maybe that. And that's going to allow me to kind of connect things up. There's my box. The point that I care about is this one here. That's clearly the point in red that I've just projected down. We can see that. So there's the point, but this is a vector that I'm drawing. To draw my vector, that's quite easy. All I do is I start at the origin, and I draw my vector to that point that I just plotted, just like I would do it in 2 dimensions. That's a pretty crummy straight line, but you'll just have to deal with it. Does that feel okay, Olivia? Okay. And they're all kind of that same way. So it's just, once you get the hang of seeing the 3 dimensions, it's a lot easier. So it just takes a little bit of practice. Okay. But you have to look at it like one of those like magic eye pictures until like the 3-dimensional pops on it. It's like, ah, now I can see it. Who's next on questions? Megan? Number 11? Oh, sure. So 11 asks to just find 3 points that are on this line. Okay. So to find points on this line, all we're going to do is we're just going to pick values for t. So I'm going to pick 3 different values of t and evaluate, and whatever I get is going to be my point. So the first value of t I'll pick maybe a 0. So when I do that, this whole last piece just zeroes out. I really just am left with -3, 8, -4. There's 1 point. Now let's say I pick t equals 1. So basically all I'm doing is just adding those 2 vectors there. So when I do that, I get 11, 17, -2. Andrew? Well, they're points, so there isn't an IB component form for a point. It's just an ordered triple. That's okay. But again, like those are not, like, that's not a dumb question, right? Like there's a lot of objects going on here that are written as triples. Some of these are vectors, which have a lot of different forms we can write them. Some of them are points, and there's just really one way to write a point. And then I'll pick a third value of t. The t's don't have to necessarily all be positive or even whole numbers. I could do something like negative. So let's do -1. So basically here I'm just going to be subtracting these 2 vectors. So that's an example of a point. And really there's nothing magic about these values of t. I just tried to pick things that would be convenient. But that's all you need to do. Is that cool? Yeah. All right. I mean, it's literally the same thing. You just pick 3 values of t. I'll find 1 point on here to get you started. How's that sound? Fair compromise? Okay. So let's just pick t equals 0. So when I do that, all the things with the t's are going to zero out, right? Everybody agree with that? So the component, or the coefficient in front of the I, is -2. And remember, the I vector is just basically the x component. And the coefficient on the j vector is going to be +6. The j's are just like the y component. And then the coefficient on the k vector is going to be 4, which are like the z component. So there's my first point. And then, just like we did before, you just pick another value for t, and you'll generate another point, and you pick another value for t, and there's another point. You can keep doing that as many times as you need, generating points. Gabe, feel good? Good. Who's next? Andrew? 13 is no, 14 is yes. Can I do 14? Sure. So 14, we want to check to see if the point 5, 8, 12 lies on this line. If you're able to do 13, what was the problem with 14? Megan? Oh, okay. I didn't know if it was like I didn't know what to do or I got it wrong or what happened. That's why I was asking. I wasn't trying to be judgy there. Might have sounded judgy. I just have a judgy voice sometimes. Okay. So what I want to check here is I want to check if there's one value of t that's going to give me my x value to be 5, my y value to be 8, and my z value to be 12, right? So remember that the I component is the x's, that the y component is the j's, and then the z component are the k's. So 12 equals 12, there's nothing really to do there. Since there's no t to solve for, that equation is true, that's good enough. I don't need anything more than that. For this equation, I'll subtract 15 and then divide by -4. That gives me 5/2. Oh, okay. Yeah. And then this one also gives me 5/2. And since the t's agree, we're good. Notice the third equation was always true, so I didn't have anything to solve for over there. But if that one had a t in it would also have to give you 5/2t for this to be a yes answer. All of the t's need to agree. We got out of jail free here because the third one was just a constant. So, Katie, you had your hand up also when I talked.
Number
8. Okay. So we're given the 2 points. And just for the sake of argument, I'm going to call this point A and B. So my vector equation for the line is this, where r0 is my point vector and v is my direction vector. So for r0, there's 2 obvious choices. It doesn't matter which one you choose, they're both correct. So I pick one of the 2 points, either point A or point B. For the sake of argument, let's use point A. For the direction vector, there's 2 obvious choices. You could do the vector AB or the vector BA. It doesn't really matter which one you do. For the sake of argument, let's do AB. So to calculate the vector AB, that's going to be the point for B minus the point from A. Everybody okay there? So if I plug this all in now, there's my final answer. Oops, sorry guys. That's -11. I just wrote it down wrong, or copied it down wrong. So that should be -4. That one's -4. No, it'll be different numbers, but they would be equivalent. The answer would be equivalent, but the numbers would definitely be different. So there's really 4 different reasonably acceptable answers for this, whether you use point A or B, and then whether you use vector A, B, or BA. Raul? Of course. Okay, so I think we've done one of just about everything here. So you guys should feel a bit better about this. I'm not going to check these in today. I know that some of us still had a lot of questions about things, so I wanted to give everybody a chance to ask some questions. And if you have things to finish up or, like do a little bit more work on, that's perfectly fine. We'll check them, this and the previous assignment in last time. So we'll do a big check next time on several homework assignments. But I felt like just giving everybody a couple more days to kind of ask some questions and go back and pick away at some more stuff would be helpful here, as I know we're getting into some things that are a little bit more complicated. There's a bit more notation going on, and probably having a little bit of extra time to work on things would be helpful. Today, we're going to start talking about planes, not like airplanes, but like geometric planes. So in 2 dimensions, we can graph points and lines, right? A point is a 0-dimensional object. A line is a 1-dimensional object. In 3 dimensions, we can graph points, lines, and now planes. A point is a 0-dimensional object. A line is a 1-dimensional object. And a plane is a 2-dimensional object. So one way to write the equation for a plane is called the Cartesian form. This is ax plus by plus cz is equal to d. Where those coefficients a, b, and c, and d are all integers. We call this a Cartesian form because it's describing the plane using coordinates on the x, y, z axis, which is often called the Cartesian coordinate system when we use an x, y, and z axis. It's named after the philosopher René Descartes, who conceptualized this framework for describing geometric objects algebraically. It was a big deal. So an example of an equation for a plane would be something like 2x plus 6y plus 3z is equal to 12. Now suppose we were asked to graph this. The easiest way to try to graph one of these things is to try to make this right-hand side equal to 1. What can we do to both sides of this equation to make that right-hand side equal 1? How about dividing by 12? Everybody okay with that plan? So when I do that, 2 divided by 12 gives me 1/6. 6 divided by 12 gives me 1/2, and 3 divided by 12 gives me 1/4. Now that the right-hand side of my equation is equal to 12, it should be easy to find some points that lie on this plane, or that satisfy this equation. So all I'm going to do is try to make this first fraction equal 1. What value of x will do that? 6. So if this fraction is 1, what do the other 2 fractions need to be?
0.
They need to be 0, right? So those fractions will be 0 when y is 0 and z is 0. Everybody okay there? Now let's do the same thing, but let's try to make the second fraction 1. What value of y is going to do that? 2. So what do the other two fractions need to be? 0. And what's the third point going to be? 0, 0, 4, right? Everybody okay there? Okay, so that's really easy, right? So if I wanted to graph this now, I'll draw my coordinate system. So in the x direction, 1, 2, 3, 4, 5, 6. In the y direction, 1, 2. And the z direction, 1, 2, 3, 4. And then to draw my plane, all I'm going to do is connect these 3 points. And then usually we kind of like shade that area. Is everybody okay with that? Gabe? Oh, stretching? Okay. Get your stretch on there, Holmes. So the vector equation for a plane is r equals m plus as plus bt. Where the m vector is just a point vector. It's any point in that plane. S is a direction vector. It's any vector that lies in the plane. And since it's 3 dimensions, we actually need 2 vectors to describe the direction of the plane. Because you have like, it's 2-dimensional object, so it needs 2 kind of directions. But t is just any other vector in the plane. So, for example, if we have the point 4, -2, 1 that lies in the plane, and we have the vector 7, 3, 1 and 6, 4, 2 in the plane, we can write the equation for the plane just as our point vector plus one of the plane vectors plus the other plane vector. And that's it. So that was a very simple example because we gave you the point that was in the plane and we gave you the 2 vectors that lie in the plane. What if we're a little less explicit and instead we give you just 3 points that lie in the plane? For the sake of notation, I'm just going to refer to these points as A, B, and C. So again, our equation for the plane is r equals m plus as plus bt. So for vector m, what are my choices? Yeah. I could use A, B, or C to create vector m, right? So that's easy still, right? Nothing really changes here. To find the vectors s and t, though, how can I find a vector in the plane from points in the plane? Well, I can just find the vector AB or BA. I could find the vector BC or CB. And I could find the vector AC or CA. I really just need to find two of these three. And it doesn't matter which direction I find the vector, whether it's AB or BA. But I can't use vector AB and vector BA, right? You have to have, I can do this one and like this one, for example, but I can't do AB and BA. Is everybody okay with that idea? So you have to use all 3 points when making your vectors, basically. So if I say vector S is equal to AB, then what we do is we take the point for B, and we subtract from it the point for A. And then if I did the point, or the vector AC, I'm going to take the point from A and subtract from it the point for C. Oh my goodness. What did I write down here, guys? Okay, who's dumb? Your teacher is. No. You know why he is? Because he wrote down all the numbers just in like all the wrong spots. I don't know what. Do you ever like do something dumb?
Yes.
Yeah, it just happened to me. That's better. Okay. And then this one would be 3, 4, negative 1. And then we're subtracting 5, 1, and 8. Okay. That's more like it. Oh my God. All right. Well, this is what I'm going to change. I did BA and CA because I'm, again, pretty dumb. Well, I'm making some stupid mistakes. It's not helping make this process that's not terribly difficult seem much more difficult than it's supposed to be. So again, just like when we write vector equations for a line and we have like infinitely many possible answers, the same thing is true for the vector equations for a plane. But realistically, like you probably wouldn't use a point other than the 3 you're given. And you probably wouldn't make a vector in the plane from points that you weren't given. So really, there's not infinitely many answers here, but there's still several that would be perfectly acceptable, and you might get different answers and have a correct answer. So if you're checking against your friends or whatever, like it's possible they have something different than you and you both did it correctly. Okay. Bless you. You're welcome. consistent on that placement. Okay. So what if we wanted to find 3 points on this plane? Remember how we found points on a line just a moment ago? You pick the values for t, right, for the parameter. Here we have 2 parameters, so we're just going to pick 2 values, one for a and one for b. You can really pick anything you want, but like, why make your life hard? So if I pick a to be 0 and b to be 0, basically those last 2 vectors just disappear, and I'm left with the point -1, 2, 4. Is everybody okay there? Now maybe I'll pick a to be 1 and b to be 0 this time. Basically all I'm going to be doing is just adding those 2 vectors. So that would give me the point 2, 2, 9. And then maybe I'll pick a to be 0 and b to be 1, in which case I'll just be adding the first and last vectors. Which gives me the point 1, 5, 2. So there's 3 points. Or did you have to find those 3 points? Nope. You can pick any values for a and b you'd like. Those are the 3 points that I would find just because the arithmetic's really easy to deal with. But, you know, like, do whatever you want. It's okay. There's no set way to do this. Everybody all right there? So another familiar sounding question, does the point lie on, in this case though, instead of a line like we did in the homework yesterday, we're going to check to see if that point lies on the plane. So if it does, then there'd have to be an equation, or a value for a and b, such that the x-coordinate gives us 15, the y-coordinate gives us -1, and the z-coordinate gives us +3. So I'd have to satisfy the equation 15 equals 8 plus 2a plus 1b. And then -1 equals 1 plus -1a plus 1b. And then 3 equals 3 plus 1a minus 3b. How many variables do I have in each of these equations? 2 variables, right? So to solve an equation with 2 variables, I have to make a system of 2 equations and solve that system. I have 3 equations though. Which 2 should I pick? It doesn't matter. You pick any 2. Just for the sake of argument, let's use the first 2. So that's 2a plus 1b equals 7. Notice I just rearranged the equation a little bit to get it in a form where I can type it into a matrix. And then I'll have -1a plus 1b is equal to -2. So there's my 2 variable system. So I'm going to make a matrix and use the RREF on that matrix. So once I've entered in my matrix, I go back to the main screen, then go back to my matrix menu, over to my math tab, scroll down towards the bottom and find the RREF command. And I do that on that matrix that I just made, which gives me that matrix. What this means then is A equals 3 and B equals 1. But this doesn't stop. The problem is not finished quite yet, because all we've found here are the values for A and B that give us a point that has x coordinate 15 and y coordinate -1. We still need to check if these two values of A and B also give us the z coordinate of +3. So the easiest way to do that then is to check here. This is the third equation that we didn't use, right? We used the other three equations. And I notice that that does indeed satisfy. Okay. So if you get an answer of no, it's possible that you wouldn't see it until you did this final check, right? You could get like a no solution here. That's possible, although rather unlikely, where you're probably going to see your failure is on the check part. So you have to remember to do that. Most of these systems, you'll get a value for A and B where you can get the first two coordinates, but you wouldn't be able to get the third one. In the case where the point doesn't actually lie on the plane, that's probably going to be the more common occurrence. Is everybody okay with that procedure? Again, not terribly complicated in terms of like computation. Just knowing what to do is kind of the hard part. The how of actually how to do the procedures, none of the procedures were terribly difficult. The hardest thing to do was solving the system that we did with our calculator. Knowing how to get that information out of the equation, that was maybe the trickier part, right? So what we're going to talk about next is how to translate between these two different representations of a plane. So how do I go from the Cartesian form of a plane to the vector form of a plane? And then also how to go from the vector form back to the Cartesian form. Everybody okay with this plan? So let's do the easy way first. So let's talk about how to go from the Cartesian form to the vector form. So let's say we have the plane 2x minus 3y plus 8z equals 24. My plan here is just going to find 3 points on the plane and then just write the vector equation from 3 points, just like we did a few moments ago. So to find those 3 points, basically I'm going to do the same thing that we did to graph this. So if I divide both sides by 24, we can see that we get the 3 points, 12, 0, 0, 0, negative 8, 0, and 0, 0, 3. Lynn? Well, 3 divided by 24 is 1/8.
Oh.
So it does look like they did switch, but they switched because that's, you know what I mean? I didn't switch them. The numbers just switched because of the division. Everybody good there? So I'm going to pick one of these points to be my point vector. So for the sake of argument, I'll just use the first one. Call these A, B, and C. For my direction vector, let's do BA. So that would just be, oops, I meant, yeah, BA. So that would be vector A, or point A minus point B. And then for my T vector, let's do CA. So that would be 12, 0, negative 3. Again, point A minus point C. Does it matter how you find those two direction vectors there? Not really, right? As long as you used all 3 points to find the two vectors, you should be fine. So then my vector equation for the line would just be M plus S times A plus T times B. And we're done. Bless you. So this wasn't so bad, right? We just had to find 3 points, and then we wrote the vector equation for a plane from the 3 points. Worth pointing out to you guys that this finding of the points could be a little bit messier than what's happened here. Notice here that 24 is divisible by 2, 3, and 8. If that were not the case, you're just going to end up with some like yucky fractions. So if like one of those coefficients was 5 or something, you'd end up with one of those points with like a nasty fraction in it, but that's fine. It's not a big deal. Like the only thing that gets a little messy is when you have to like add or subtract the vectors. You might have some fractions to add or subtract, but like it's not so really that bad. But just as a heads up that it could get a little fraction yucky there. All right. So let's now talk about going from vector to Cartesian. And this is the way that's a little bit more involved. But I'm going to start this process just like I started the previous one. So I'm going to start by generating 3 points that lie on the plane. Now to do this, it's a little bit different than the previous problem because here I'm going to pick values for A and B. So I'll start with picking both A and B to be 0. Then I'll pick A to be 1 and B to be 0. And then I'll pick A to be 0 and B to be 1. So far, so good? Okay. So I just generated 3 points. Now remember, my Cartesian equation for a plane looks like this, right? Everybody agree? How many variables do I have here? 4. I have A, B, C, and D. But I only have 3 points. So we have 3 equations that I can make, but 4 variables. That's a problem, right? So what I'm going to do is I'm going to do a little trick to reduce the number of variables in this problem. The trick is going to be the same one we did to graph this. I'm going to divide both sides by D. And you might look at this and go, yo, Mr. Kulik, you still have 4 variables in this. What good did this do? Well, here's the trick. Here's the trick. The A, B, C, and D are all integers. That was a requirement for this formula. So A over D is really just some fraction, right? Yeah. I'm going to call that fraction little a. B over D is just some fraction. I'm going to call that little b. And C over D is just some fraction. I'll call that little c. So now I have an equation with 3 variables in it, and we can proceed. So you don't really need to show this work when you're doing it, but I want to explain to you how I went from this form to this form and why we're worried about doing it. Okay? All right. So now, if I'm going to use my 3 points to create 3 equations by plugging in the x, y, and z into the appropriate places. So my first point was 3, 2, 1. So I have 3a plus 2b plus 1c is equal to 1. My second point was 4, 7, negative 1. So I have 4a plus 7b minus 1c is equal to 1. And my third point was 0, 7, 2. So that's 0a plus 7b plus 2c equal to 1. So there's my system. To solve this system, I'm going to use a matrix. So the matrix that I would convert this to is 3, 2, 1, 1, 4, 7, negative 1, 1, 0, 7, 2, 1. And then I'll go to my calculator and I'll enter this stuff in. Which I've done. So I'll go ahead then and retrieve the RREF command and do that on matrix B, my new matrix that I just made. Notice I'm getting some stinky looking decimals there. I can use the math and then fraction command on my matrix, and it'll rewrite this with the fractions in it, which is going to be better for me. So what this tells me is that A is 1/5, B is 1/15, and C is 4/15. So if I plug this back in, I have 1 over 5x plus 1 over 15y plus 4 over 15z is equal to 1. And I have one last little final step, is I want to clear the fractions out of this equation. So how would I do that? Multiply both sides by 15. Yeah. So 15 times 1/5 is 3. 15 times 1/15 is 1. 15 times 4/5 is 4. And 1 times 15 is 15. So there is my Cartesian form. Okay. Is everybody happy with that? Let's stop here. That was a lot.